So here's a nice thought puzzle. It says this: a missile is launched from the surface of the Earth, but we're going to say it uses all of its fuel up in an initial burst, and then it's going to coast the rest of the way, so that the only force it experiences, if we ignore air resistance, is gravity tugging it, slowing it down. Okay. As it rises, what happens to the kinetic energy? And what happens to the orbital potential energy? That's a good question. You know what? This is one of those two-column multiple choice questions. I'm going to read this vertically. So first of all, what happens to the kinetic energy as it rises? Does it increase or decrease? Well, we said we're firing all the fuel at once, and it's going to coast the rest of the way. How will it behave if it starts to coast away from Earth? Will it speed up, slow down, or stay the same? Why will it slow down? You're right. Why? But why? Oh, unbalanced force, gravity. Yeah, if we do a free body diagram, we would have gravity. It's a bit tricky. It's a constantly changing force of gravity, which without calculus we have a tough time dealing with. But so, does the kinetic energy increase or decrease? What about the potential energy? Why? And also because of the law of conservation of energy. The energy's got to go somewhere. If it's losing kinetic, it's got to be increasing potential. So, yes, no, and as Aiden blurted out earlier because he wants some glory, it's got to be C. Yeah, he's right. I like example 4. This is also going to be a long question. A satellite this is rocket science. I can try and make it easy to understand, but we're stuck with the numbers the universe gives us. And for Pete's sakes, it's rocket science. Not like that's considered, an easy thing to compare other things to, right? An 1,800 kilogram satellite is placed in a stable orbit. Okay, the fact that it says that tells me a couple of things. First of all, last day, Kai, you were away, but we did a question where we just lifted it up, not putting it in orbit. Because we were just lifting it up and not putting it in orbit, we said we'll assume there's no change in kinetic, that it started and ended at rest. It was just hovering there because, invisible leprechauns or fairies are holding it above the Earth. Here, now we're in orbit, a stable orbit. That means not only are we going to have some potential energy, we're going to have some kinetic energy too. Oh, of course we are, because we're going at 4,200 meters per second. It's going to be a half mv squared. All right. Darwin, what's A want me to find? Did you say orbit? Did you say orbit? Yeah. If I'm in orbit, I can say gravity is what's pulling me in a circle. I haven't started doing energies yet because I don't know if I need to yet. By the way, I think for part B I might start doing some energies because I see how much work. But for now, I can say this. Which equation for gravity? We're going cosmic, so we'll use universal gravitation. Big G, big M, little m over r squared equals little m. Which version of AC am I going to use? The one with the V or the one with the T in it? How do you know? They gave me a V, so it's going to be V squared over R. One of those cancels. One of the R's cancels. In fact, we did this one often enough. You might inadvertently remembered it. It turns out, no. I want to get the R by itself. I was getting the V by itself. No. Okay. Where is the remaining R on the stuff moves diagonally? I think R is going to be big G, big M over V squared. Is that right? I think. So, R orb, the orbital radius, is going to be big G, 6.67 times 10 to the negative 11. Big M, it doesn't say another planet, so assume Earth unless the question says different. The only thing I'll probably put one question on your test on the moon, because I dream of us having a moon base someday. And you have all the data for the moon that you need. But for now, I've memorized that the mass of the Earth is 5.98 times 10 to the 24th. That's right on my formula sheet. Divided by 4,200 Don't forget the squared. And I get an orbital radius of 2.26 times 10 to the 1, 2, 3, 4, 5, 6, 7, I think. I'm going to store this on my answer button. In fact, I might even, if there was a part C and a part D and I knew I was going to be using this over and over, I might write out the whole thing so that I can use it later. But for now, I'm going to go 2.26 times 10 to the, what did I say, 7th. And that's a radius, so it's in meters. Xavier, what does B want me to find? Oh, that's easy. Don't write this down. I can just go force times distance, can't I? Oh, because the force is changing? Well, it's also the area under a force versus distance graph. Did they give me a... This is why I taught you the work energy theorem. The best definition of work, but also the least convenient, Zach. Work is the change in potential plus the change in kinetic. I don't do these both at the same time. What do you want to find first? Change in potential plus change in kinetic. Doesn't matter, pick. Change in potential. Okay. So, what's change in anything? This is going to be negative big G, big M, little m, over R final minus negative big G, big M, little m, over R initial. Is it R or R squared on the bottom? Which one has the R squared on the bottom? Force and little g. And is it easy to get them mixed up? Yes. So just be really meticulous on your formula sheet. Okay. This is going to be negative. What's big G? I'm going to stop writing out the 6.67 times 10 to the negative 11. I'm just going to put the big G there, and I'm going to say we all know that that is 6.67 times 10 to the negative 11. I'm going to save myself some writing. Mass of the Earth, I'll plug in, 5.98 times 10 to the 24th. Ooh, what was little m? 1800? Divided by R final. Ah, that's for the 2.26 times 10 to the 7th. But I'm going to use my answer button there. Xavier, what do you notice about a minus minus? They're plus. What do I have on the top of the first fraction? A big G, a big M, and a little m. What do I have on top of the second fraction? A big G, a big M, a little m. This is where I said I'm going to actually use ditto marks. Times that, times same thing, times same thing, times same thing. The only thing I'm going to change is our initial. What was our initial radius? The radius of the Earth. What point? What? Okay. Whew. I'm going to type in the first term, write that one down to like 5 sig figs, backspace, edit, and then do the second term. I'm not going to try doing this all at once. So I'm going to have negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 1800 divided by 2.26 times 10 to the 7th. I get negative, there's a 0 after that. That's a good place to go to. Negative 3.1768 times 10 to the 10th. Plus, and now I'm going to backspace and edit. I'm going to delete the negative. And on the bottom, instead of 2.26 times 10 to the 7th, 6.38 times 10 to the 6th. I get positive 1.1253 times 10 to the 11th. Now let's add those together. Negative 3.1768 times 10 to the 10th plus how? I can just go answer button. That's a bonus. And I get how much rocket fuel, how much energy from rocket fuel in joules was used just to get to the right spot. 8.0765 times 10 to the 10th joules. 8.0765. 8.0765. That's how much rocket fuel joules it would take just to get me to the right spot. Am I in orbit yet? No. What else do I need to stay in orbit? I need the right orbital velocity, the kinetic energy. So we just found the change in potential energy. What else do I need to find? Change in kinetic energy, which is going to be a half mv final squared minus a half mv initial squared. Are any of these zero? What did we decide that we're always going to be launching our rockets from? North Pole. Superman's Fortress of Solitude? Yes, that's where it is in the comics, Mud. Or Santa's Workshop. So Santa's got a good rocketry program. He must. How do you think he gets those presents all around the world in 24 hours? What that means is we can assume that VI is 0. So it's just going to be 0.5 times little m, 1800, times 4200. Don't forget the squared. How much kinetic energy do we need to give this rocket ship? 0.5 times 1800 times 4200. Don't forget the squared. And I get 1.5876 times 10 to the 10th. What? Oh, we're still not done? Ugh. No pun intended, but this is a lot of work. Yeah, we're going to add them. It's going to be the change in potential, 8.0765 times 10 to the 10th, plus the change in kinetic, 1.5876 times 10 to the 10th. I've been challenged to try and do this one in my head. They're both 10 to the 10ths, so the decimals are in the right place. So it's going to be something like this. 8 plus 1 is 9, 9.5, 9.57, 9.65, 9.66 times 10 to the 10th? 9.6 something times 10 to the 10th. There you go. Since you challenged me. Joules. Although I quit at 3 sig figs and didn't bother going further, so I did a pretty good approximation in my head. Okay. This will be about the second longest question I can ask. What's the longest question I can ask? Instead of giving you the orbital speed of 4200, I can make you figure it out by just giving you the radius. I'm not going to do one like that on a test. I used to. It just takes up so much time. Now that we used to have 80-minute classes, and that was enough time for you to make a mistake on a test and still recover. Because on here, it's almost always calculator mistakes. Why did I get a negative? Or something. And you could recover. Now I'm having to be a little more judicious. Mr. Dewick, what, Gabor? Mr. Dewick, what, Gabor? How do you build a Death Star? That's a great question. Put your pencils down. Look up. Since you asked. Turns out the physics of how to calculate how to build a Death Star are pretty trivial. It's high school. We've done it all already.
I was just reading about this petition earlier this year to the US President to build a Death Star.
So there was a time when the White House had a sense of humor. No editorializing, but there was also a stretch of 4 years where it didn't have much of it. Anyways, in 2016, a petition started, whitehouse.gov, and if enough people sign the petition, the law says the White House has to respond with a statement. That's all. You're not getting the petition, you're not changing the law, but they at least got to acknowledge it. Okay? So somebody decided to start a petition to build a Death Star, and of course, all the nerds piled on, and it got enough votes that the White House had to respond with a statement.
To the US President to build a Death Star. And so that got me to thinking about, what if we did actually build a Death Star? So the Death Star is the implement of destruction in Star Wars movies that floats around and blows up planets. We've got the International Space Station up there at the moment, but let's stop messing around and replace it with the Death Star. Let's scale up a bit. So the first obvious question is, how big would it look from down here on Earth? And the answer is enormous, actually. It would be about 45 times the width of the full moon across if you just looked up at it. So it would be by far the biggest thing in the sky. So it's about, according to the specification, you have to go and read on the Star Wars websites and find out exactly what the technical specifications are if you do decide to build your own Death Star.
We're talking about the original Death Star from the first chronological Star Wars movie that came out in 1978-79, which is Episode 4. Because they've apparently run out of ideas, so they built several more Death Stars in Star Wars movies, because that seems to be all they can think of. Yeah, I said it.
And if you do, it works out that it's about 160 kilometers across. And so if you do that and then put it in the low Earth orbit that the International Space Station is, which is about 400 kilometers up, it's actually absolutely huge. And actually you run into a few problems, because 400 kilometers up, if you build something 160 kilometers across, that's a decent fraction of the distance back down to the Earth again. So you're going to start worrying about whether it's getting back into the atmosphere. So you might want to push it a bit further away rather than putting it quite as low down as the International Space Station. But if you're going to build a Death Star, you want to kill things, right? You want to blow things up. And
do you want to kill things and blow things? Yes, you do. I can see it in your eyes. Okay.
So the big thing about the Death Star is this laser cannon that it's got that it uses to explode planets with.
A super laser.
A super laser, pardon me. Yes. So again, if you go back to the technical specifications for a Death Star, it's not very clear about how powerful this super laser actually is. But you can figure it out just by watching the film, because it actually destroys a planet kind of about the size of the Earth. And it fires for just a couple of seconds, and in that couple of seconds that provides enough energy to basically vaporize the planet, to send it all flying apart.
That was Alderaan, that planet.
Oh, pardon me, yes, the planet of Alderaan. And so actually, you can just from that one piece of information, you can figure out.
Conveniently, if you look at the Star Wars wiki, Alderaan almost the same size as the Earth.
How powerful the laser has to be. So the way this works is, it basically destroys the planet by making it all fly apart. And the amount of energy you need to make a planet fly apart doesn't matter how you do it. The amount of energy is the same if you do it explosively in that way, or if you did it sort of the slow way of just taking the planet apart bit by bit. And so you can figure out how much energy you need to completely destroy a planet just by doing the thought of experiment of what would happen if I took it apart bit by bit. You can calculate the total energy you need to destroy a planet on that basis, but if you want to know what the power of the laser is, that's how much energy it gives per unit time.
Powers work over time.
So if you want it in watts, that's joules per second, energy per unit time. And so actually, if you want to figure out the power of the laser, you need both the amount of energy it delivers, but how long it takes to deliver it as well. So I sat there and timed it, yeah, and this whole thing is going to be very back of the envelope, order of magnitude type calculation, because it's really not worth trying to do this calculation terribly carefully. But basically, it fires for a couple of seconds, so it's which is accurate enough for these purposes.
Okay, so T is going to be 2 in our power equals work over time. T is 2.
We need to do the maths now if you want to actually figure out what the energy is. So if I have a planet and I want to start taking little bits of it out, so supposing the planet will give it a mass big M, and I want to take out the first little mass, so we'll call this little M1. I want to take that little bit of the Earth and kind of pull it away, all the way off to infinity, or just a long way away.
Off to where? Oh, okay.
The amount of energy I need to put in to do that is given by one of Newton's laws, and it's basically G(m1)m over little r.
That's the potential energy equation, except they've left off the negative because they don't want to confuse the audience. So we're just doing a magnitude calculation here anyways. Okay?
Okay, so that was one little bit. And then I can, take the next little bit away, and then I have to do the same thing again. So you're not with G, so I need to add a bit more energy. to pull it that bit apart, M2 over R, and so on. Just keep doing that. And I can rewrite this equation, if I want to, as G times big M divided by little r times all these little sums here. And then all the other bits as well. But
oh yeah, there's a GCF there. You factor out the big G, the big M, and little r, and you'd be left with little m1 plus little m2 plus little m. But wait a minute. What is little m1 plus little m2 plus little m3 plus little m4 plus little... Same as big M. So a better way to write this would be big G, big M squared.
Of course, when I've taken the entire planet away, that's going to be the mass of the planet, this whole lot. So the formula I'm going to end up with is G times M squared divided by R.
That's how much energy you need to vaporize a planet. Well, no, there's some challenges with this because technically, as you're pulling mass away, you're also weakening gravity. And so probably there's some kind of number, some coefficient in front of this, like maybe a 0.8 or a 0.6 or something. But we're close.
Now, this is a little bit of a fraud because this is the R that you start from. And that's the
Oh
R.
yeah,
that goes
R
in
would be
there.
changing.
Of course, as I'm
as
digging away
planet
more and more of the
away,
planet, R's getting smaller and smaller because I'm getting closer and closer to the centre. And actually, M's getting smaller and smaller as well because there's less and less mass left behind to kind of pull back on the bits that I'm pulling away. Because that's what I'm doing, is pulling away against the force of gravity. And so this formula isn't exactly right. It's just approximately equal to that, and there's some numerical factor out in front of it, but it's probably right to within a factor of 2, which again, for the purpose of these kind of calculations, is entirely adequate. So if I want to figure out to destroy an Earth-like planet, if I put the symbol for the Earth here, cross with a circle around it, and the symbol for the Earth down here, that's basically the energy I would need to expend to destroy an Earth-like planet. Gravitational constant times the mass of the planet squared, mass of the Earth squared, divided by the radius of the planet, the radius of the Earth. If you basically
how much is it? Get your calculators out. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th squared divided by 6.38 times 10 to the 6th. I didn't stop the video soon enough. You saw a little bit of the punchline. It should start with a 2, I think, or be really close to a 2. 6.67 times 10 to the negative 11. Sorry, I'm not showing this on my YouTube calculator, but I got a video going right now. 5.24 times, no, 5.98 times 10 to the 24th, Mr. Dewick. Squared, divided by 6.38 times 10 to the 6th. I'm getting, you get 3.738? Yeah? Okay.
energy I would need to expend to destroy an Earth-like planet. Gravitational constant times the mass of the planet squared, mass of the Earth squared, divided by the radius of the planet, the radius of the Earth. If you plug all the numbers in for the Earth, that works out at a few times 10 to the 32 joules. So that's like 2 or 3 with 32 zeros after
Is
it.
rough.
And of course, remember, it actually took a few seconds. So basically, the power of the laser then has to be about 10 to the 32 watts. So that's 1 watt.
If you say instead of t being 2, if you let t be about 3.7 seconds, it cancels. Basically, the energy involved here is 10 to the 32 watts. How big is that?
32 zeros after it.
Sorry, the
So to put it in perspective, the most powerful laser in the world, which is actually Lawrence Berkeley Lab, which they're using to accelerate electrons, that's 17 orders of magnitude less powerful. So the most powerful laser in the world is 17 orders of magnitude, that's 1 with 17 zeros after it times less powerful. Or in other words, I would need 1 with 17 zeros of these lasers if I wanted to generate the laser power of one Death Star.
So that seems hefty.
And actually that's not the worst of the problems, because then even if I could build such a laser, then I need the energy to power it. So I was thinking, now how could I power my Death Star? And electricity seems like a sensible way of doing it. So I went and looked up what the total power generation capacity of the Earth is. So where are all the power stations on Earth? And if you were to take all the power stations on Earth and put them to work to generate enough energy to fire this laser once, then you'd actually have to set them to work for a few trillion years. So which is what, 100 times the lifetime of the universe to actually just get the thing to fire once.
Well, that's not going to happen.
And that's not going to happen. But again, I messed up, right? Because I should have looked in the technical guide as to how to build a Death Star, and it says actually a Death Star isn't powered by electricity; it's powered by a thing called hypermatter.
What's hypermatter?
I have no clue, but I can.
You must know what it is. You're a physicist.
It is a creation of science fiction, I believe. Even though I don't know what it is, I can at least put an upper bound on how good it is, right? Because I know that the maximum amount of energy I can get out of anything is given by Einstein's famous equation E equals mc squared. So I could figure out what the most efficient way I could possibly generate the energy needed to fire the Death Star once by using that formula. I know what the energy I need is, I just plug it in, that then tells me how much mass I need to completely annihilate in order to generate that much energy. And it works out that's about 10 to the 15 kilograms, one with 15 zeros after it, kilograms, which turns out to be almost exactly the mass of Mount Everest. So every time you fire your Death Star, you've got to completely vaporize Mount Everest's worth of mass.
There seems something quite poetic about the fact that you would need the largest mountain on Earth to destroy the Earth.
Yeah, it has a certain ring to it, doesn't it?
So, theoretically, could you build a Death Star? I mean, we ran the numbers, sure, but not with anything remotely resembling our current level of technology. And even if you're trying to stay, removing hypermatter, if you're trying to stay within the bounds of our universe, it's tough. When does this class end? This class ends in 25 minutes. Okay. I was going to try and start the next lesson. I'm going to press pause. I'm going to say, can you please try number 2? Number 2 is just saying calculate the orbital potential energy of a 12,500 kilogram rocket on the surface of the Earth. Just use the cosmic version, and you should get a negative answer. How do I know? Because this rocket is not out at infinity, so it's got to have less energy than 0. Number 3. Number 7. Number 9. Number 10. Number 14. And number 15. Believe it or not, we're technically done the unit. I'm not going to be teaching you anything new. I'm just going to be showing you some applications. So if you want to, you can now start whittling away at the ultimate gravitational review, the gravity review that I gave out. It's a shorter unit. I'm thinking right now our test is not going to be next week. It's probably going to be the beginning of the week after. I do want to talk about escape velocity and black holes because I find black holes very attractive. Nothing?